Welcome to part 3 of 201D. By now you should have a basic understanding of what an inductor is, what inductance is, and what induction is. And we should understand each one of these concepts. Now we're going to look at the effects of an inductor inside a DC circuit and break it down a little bit more about what is actually happening as we open and close our circuit. When we have an inductor in DC circuit, we have to remember one thing. Our inductors are not pure, therefore they have both resistance and inductance. But we're going to treat them a little bit differently. We're going to look at them from the perspective of a pure inductor. First of all, if I consider my DC circuits to have only resistance, what I know is that when I close the switch on my purely resistive circuit, I'm going to have an immediate current rise all the way up to the maximum value. Remember, in a DC circuit, my resistance is determining what my maximum current is going to be. So therefore, in my DC circuit with only resistance, I will see maximum value as soon as I close the switch. If I had a circuit in DC that was a pure inductor without any resistance whatsoever, what I would find is that the current rise would be slowed down. It would not be instantaneous. However, since there's no resistance anymore, I don't have any maximum. So as my current rises, it will rise in an arc, and that arc will depend on how much inductance is there. The higher my inductance, the longer that arc is going to be. The lower my inductance, the sharper that arc is going to be. Let's look at these three different types of circuits. Firstly, my purely resistive circuit, as we mentioned, as soon as I close my switch, it goes from 0 to maximum current, and it will stay there until I open the switch again. When I have a purely inductive circuit, it will slowly rise from 0 and keep rising and rising and rising. And since it has no resistance, it has no maximum. So therefore, current will eventually just keep rising until it's out of control. In a true coil, I of course have both resistance and inductance at the same time. So when I mix these two together, this is what we actually see inside a DC circuit. We have resistance, which gives us a maximum value. However, we also have inductance, which slows down the current rise. So we both see a smooth arch that's created by the inductance, and then we have a maximum current level that's created by the resistance. When we look at the curvature that is created by a system with both inductance and resistance, we can break that curvature up into 5 separate parts, and each one of these parts is considered to be a time constant. The amount of time that it takes to get from 0 up to a steady current will take 5 time constants. And the amount of time it takes to get through each time constant is dependent on both the inductance and the resistance of that circuit. The formula that we can use is T is equal to L divided by R. So one time constant value is equal to the inductance divided by the resistance. Let's take this circuit for example. With this coil, I have a resistance of 6 ohms and an inductance of 0.3 henries. If we wanted to find out how long it's going to take to get from 0 amps up to maximum ampacity, we need to take the inductance and divide it by the resistance. This will give me the time period for one time constant. If I then take that value and multiply it by 5, it will give me the total time it will take to get up to full current. If I take my time constant formula of 0.3 henries and I divide that by 6 ohms, I find that each time constant is going to be equal to 0.05 seconds. And if each time constant is going to be 0.05 seconds, adding them all together will give me 0.25 seconds. So with this circuit, it would take me 1/4 of a second to get from 0 amps to a full steady current. What is interesting is that after the end of each time constant, not only can I predict the amount of time that's going to elapse, but I can also predict how much current should be flowing through that circuit at the end of each time constant. When it comes to inductive circuits, at the end of each time constant, I should have the total value of 63.2% of the total ampacity that's going to be risen. What this means is that if you take the circuit we have on the screen, I have a total expected rise of an ampacity of 6 amps. That means after one time constant, I can expect my circuit to rise to 63.2 of that 6 amps. And that value is 3.792 amps. For my second time constant, I'm going to rise whatever's going to be remaining. So after I've risen the initial 3.7 amps, I still have 2.2 amps remaining. My second time constant will be 63.2% of the remaining 2.2 amps, which gives me a rise of 1.395 amps for a total rise after my second time constant of 5.817 amps. My third time constant is again going to be 63.2% of the remaining rise as expected. So if I take the 0.813 of my remaining ampacity rise, multiply by 6.32, I will get 0.514. I can add that to my other totals, and after 3 time constants, my ampacity should be 5.701 amps. I do the same thing again for my fourth time constant, multiplying the remaining rise by 63.2, and after my fourth time constant, I'm at 5.89 amps, which leaves me 0.11 amps remaining, 63.2% of that, and added to the rest of them means after 5 time constants, I have an ampacity of 5.96 amps. I'm expecting a total current of 6 amps. However, it is accepted that after 5 time constants, the change after that is so imperceptible that we've reached a steady state of current rise. If we understand what happens in a DC circuit when I close the switch and the current rises from 0 to maximum over 5 time constants, we have to think about what happens as well when we open the switch. We don't see a gentle curve back down, or rather, we're going to see an instantaneous drop of current. Since opening the switch interrupts the flow of electrons, there is no gentle slope about it. However, what we do have to think about is the amount of induction that happens. When I open the switch, I go from maximum current to 0 current nearly instantaneously. That's a massive amount of change over a very short period of time. If you remember before, the amount of EMF is dependent on not only the amount of current that's being changed, but also by how fast it's going to be changed and how much inductance is inside the coil. Therefore, with this particular circuit, if I have 4 amps running through this coil and I open up that switch, I will have a 4 amp change almost instantaneously. And the instantaneous value we're going to use here is 0.4 times 10 to the power of 6. I then take that, multiply it by the inductance, and what I find is I actually get 2 megavolts across that switch. This only happens while the current is changing, so it is almost instantaneous and it's only for a very short duration. However, that's enough voltage it could still damage the switch by causing severe arcing. This is in fact the same principle that we use in order to have spark plugs in automobiles and any other internal combustion engine. In order to overcome this, I need to install what is called a discharge resistor inside my circuit. What the discharge resistor does is it gives me an alternative path. It's sized high enough that it's not going to really affect the current flow of my circuit. However, since it is there, it does give an alternate path for electrons to flow. Therefore, when I open the circuit this time, I'm still going to have an induction happen. However, with that 100 amp resistor and creating a secondary path for the current to flow, I won't have that 2 megavolts of voltage across my switch anymore. I will still have a voltage across that resistor. And what we find is, if I have 4 amps running across a 100 ohm resistor, I will have a potential of 400 volts across that discharge resistor. This is going to prevent any damage to my circuit, and it's going to give me a safe way to dissipate that energy. And remember, that's only happening while the current change is happening, so it's almost instantaneous and then it's dissipated. This is the end of 201D, Part 3. Now you can return to Blackboard and do the worksheet as well as the self-assessment. Make sure you're reading through the module, and if you did not understand any of the topics in this discussion, please make sure you reach out to me and get some answers. Once you're confident in continuing forward, go on to Part 4.